Before, we learned to classify acids and bases as Branson, Lowry, and Lewis. Practically, we usually don't care which of these categories acids and bases fall into. Instead, we care how well an acid or base reacts. So we classify acids and bases as strong, weak, or terrible. Looking at the structure of an acid and base, like hydrochloric acid or ammonia, there's really no way to tell if a species is strong or weak. The way we can tell is by looking at the reaction of the species with water. If all of the acid or base reacts with water, then we say that it is a strong species. If only some of the acid or base reacts with water, then we call it a weak species. And lastly, a terrible acid or base barely reacts with water. In fact, it reacts to such a small extent that we say that it doesn't react at all. Let's first take a look at acids. As we learned in the equilibrium unit, every chemical reaction is an equilibrium reaction. For example, if we react an acid like hydrochloric acid with water, the products are hydronium and chloride ions. The equilibrium constant equals the concentration of the products over the concentrations of the reactants. Remember that we do not include liquids or solids in these calculations, so water is not included. We add an A as a subscript to show that this is an equilibrium constant of an acid. So let's estimate the Ka of hydrochloric acid at 25 degrees Celsius. Let's say we start with 1 mole of HCl. We know that hydrochloric acid is a strong acid, so almost 100% of it will react with water to form products. In fact, only about 1 times 10 to the negative 6 moles of hydrochloric acid will remain, so we can estimate that we form 1 mole of hydronium and chloride ions each. If we assume that this is all happening in a 1-liter solution, we can easily convert the moles to concentrations and plug them into the equilibrium constant equation to see that the numerator is much bigger than the denominator, by several orders of magnitude. In fact, the numerator is about 1 million times bigger for HCl than the denominator. So, as you can imagine, the Ka is a very large number. Specifically for hydrochloric acid, it is 1.3 times 10 to the 6. A large equilibrium constant with a positive exponent is common for all strong acids and bases. Now, let's take a look at a weak acid like acetic acid. Acetic acid reacts with water to form hydronium and acetate ions. The equilibrium constant will equal the products over the reactants. Unlike strong acids, weak acids remain mostly in their unreacted form. In fact, if we had a beaker of 1 liter of water and added 1 mole of acetic acid to it, we would end up with 0.9958 moles of acetic acid, which is almost the amount that we started with, and 0.0042 moles of both acetate and hydronium ions. Let's calculate the equilibrium constant and see how it differs from that of a strong acid. The equilibrium constant is the concentration of the products divided by the concentration of the reactants, which ends up being 1.8 times 10 to the negative 5th, which is the equilibrium constant for acetic acid. In fact, it is typical for weak species to have small equilibrium constants with negative exponents. As we can see, there's a very large difference between equilibrium constants for strong and weak species. So we can easily predict whether a species is strong or weak based on its equilibrium constant. Now, let's take a look at a third class of acids, what we call the terrible acids. These are species that do not react with water and remain mostly in their unreacted form. An example of this is ethanol. If we were to put 1 mole of ethanol into 1 liter of water, only 1.14 times 10 to the negative 8 moles of it would react. This amount is so very small that in fact ethanol does not even react like an acid. And that's why we call it a terrible acid. We can once again calculate the equilibrium constant, which will be the concentration of the products over the concentration of the reactants, and it will equal 1.3 times 10 to the negative 16. Now, it might not seem that the equilibrium constant for weak and terrible acids are that much different, but in reality, the equilibrium constant for acetic acid is 10 billion times greater than that for ethanol, and that's a big difference. And so, because terrible species barely react, they have very small equilibrium constants. Bases follow the same exact trend as acids do. Strong bases react completely in water, and so they have a very large K value with positive exponent. The only difference is that since these are bases, we add a B subscript to the K to make it a Kb. Furthermore, weak bases have very small Kb values with negative exponents as we expect, and terrible bases have even smaller Kb values.